Loud. Okay. Go ahead.
Okay. I'm going to share my screen. Once again, Amy, thank you so much for the invitation. Thank you everyone for attending. I'm going to talk about TileDB and what we have been doing for the past several years. I hope you find this relevant. And most importantly, you know, the intention of this presentation is to just spark the conversation and get you guys to talk to us, give us your insights around what we're saying, what resonates with you, what concerns you may have, so that you know, we get our software to be better in the future. A few things about who we are, if you have not, if you did not attend the previous session we had here at the ESIP about TileDB. TileDB was a research project that I had started at MIT and Intel Labs in 2017. It has deep roots at the intersection of high performance computing, that was from Intel Labs, databases, because I was working with the MIT database group, and data science, because we had a lot of interaction with scientists throughout the course of building the system. We've raised over $20 million. So we are well capitalized. We're hiring and we're scaling the team. We have close to 40 employees so far, and we mostly hire engineers for building the system, but also domain experts, because we're working very, very closely with the sciences, and that's the way we target at the various problems. We don't just build a database. We work very, very closely with the scientists in every different discipline, so that we gain knowledge and build the system tailored to them. So far, we have a lot of traction with very diverse organizations, which proves our point for what I'm going to tell you about on universality. But we have a lot of geospatial use cases, and I'm going to share some of them today. So here's what we're trying to do with this deep dive. Well, it's not going to be exactly a deep dive, because we will try to constrain it to 30 minutes so that we can answer some questions from you guys. The agenda, I'm going to vision on what we call database universality or data management universality, and of course the motivation behind it. I'm going to present to you the secret sauce in TileDB. So how do we achieve that? I'm going to present the architecture and some very basic features of TileDB. We're going to give a lot of emphasis on global scale data and code sharing. Amy, I saw your notes from the previous email. I know that sharing data and notebooks and making them discoverable is super important for the community. We understand that. We had this on our roadmap for a long time, and of course we built it. So we're going to show it to you. We're going to explain exactly how it works. And of course, we're going to give you some use cases and examples. I'm really hoping that I'm going to cover most of that stuff. And of course, Seth and Norma are going to give you a very nice overview of the product and of course, the capabilities and use cases. Always, you can find us on Twitter, follow us, tweet something about TileDB. We're very accessible. We respond to any kind of question. So please direct anything to us, and we're going to be back to you immediately. All right, so here's the problem in a nutshell and why we built this. And of course, I'm hoping that this is going to resonate with the geospatial community, but we are going to make it more specific to the geospatial community to see how this tailors to it. What we observed while talking to organizations, and organizations across the board, not only on the geosciences, but also in healthcare, for example, we're seeing that most of the organizations working on extremely important problems are lost in the noise. And the reason is that there are way too many file formats, and thousands or hundreds of thousands or millions of files just lying around in cloud buckets. There is a metadata hell surrounding those flat files. And this is because there's no management system. It's just a file format with, you know, and the bucket with just myriads of files in it. So you need to have some metadata attached to each of the file in order to make sense of them. The data sharing became extremely complex. I mean, access control is one of the things that the database does well, but in the scientific domains we have been working with, they don't use a database because they don't have tables, and therefore existing databases just don't fit the application. So data sharing becomes extremely complex. You just need to build specialized systems just to share the files or parts of the files that you have in the buckets. And as a consequence, what we observed is that there have been thousands of data and machine learning companies and open source tools that got created. And hence, this is the noise that got created that I'm talking about here. Organizations that are comprised of scientists and they don't know the data engineering part, they just don't know what to do. There are just so many tools with different nuances across the systems, a lot of overlap, and this exacerbates the problem. If you try to make an X-ray of every single system that is out there, you're going to see that there is a lot of reinvention of the wheel. Just check out all the databases, just the SQL databases. I'm not going to talk about the formats, and of course I can, but just focus on the databases, and you're going to see huge reinvention of the wheel along the way. Because there is a huge engineering overlap, you still need to lay out the data somehow in some serial order. You need to chunk it in order to compress it. Then you need to compress it very fast. Then you need to parallelize the I/O in some cloud store. It's the same thing again and again. And just because there is a little twist in the system, people reinvent their whole stack. That's what we're saying. Like, there is a huge overlap in the software stack when addressing a problem in LiDAR versus a problem in SAR versus a completely different problem in, for example, genomics. It's the same. There's a huge overlap. And of course, scientists spend most of their time as data engineers, again, because they don't have an off-the-shelf solution. So they either build something in-house or they're trying to piece together 20 different systems. And as a consequence, organizations lose their time and money, but most importantly to me, science is being slowed down. You understand that, right? Instead of catalyzing, instead of improving the methods that accelerate science, we're actually slowing down science because of this noise. So that's the problem. So what is the solution? We envisioned to build a system with efficient, and emphasis on efficient. We're not aggregating solutions. We're building an efficient system that can support all types of data. So LiDAR and SAR and weather and imaging and any other data type you can imagine. All types of metadata and catalogs. Once you have a storage layer for all the data types, you need to make them discoverable as well. All storage backends and computer hardware. Yes, it is going to be cloud optimized, but it needs to work on all cloud vendors, but also on the laptop, also on some modern hardware of the future, like non-volatile memories, for example. It should support all APIs and tool integrations. It should not be Python only. It should not be R only. It should cover all of the languages. And of course, since we coin it as a database, it needs to have some fundamental features of the database, which is authentication, access control, right? Everything around security, compliance, and all of that. And of course, logging for auditing. This is part of the system. It should not be an afterthought. And of course, it should scale. And when we say infinite scale, we mean infinite bounded by the machines we can rent on Amazon, or the machines we can buy, or in general, the machines we can spin up. But it should support all computations. It should support SQL, but also machine learning, also linear algebra, also something custom, right? And again, emphasis on global sharing and collaboration and monetization. And although these three things may seem a little bit disparate, please trust me when I tell you they are not. They're part of these processes that the database does very, very well: authentication, access control, and logging. And Seth is going to show you how this works on TileDB Cloud today. What are the benefits from this? Well, you will have a single data platform to solve big problems with diverse data. I don't know, we mentioned dark shift detection, and this can be done by overlaying AIS data on SAR. Well, if you have two different databases or data systems, one for SAR, one for AIS, how are you going to coordinate those two? How are you going to create shims that are efficient, that take the point cloud data to overlay on imaging data, right? This is just a very simple example. It spans across so many domains. And then you're going to have a single data platform for authentication, and access control and auditing. Again, if you have one system for SAR and one system for AIS, how are you going to define access policies universally in a unified way for both SAR and AIS data? You will have to build two different access control systems if those systems are different. Of course, easy global scale collaboration of data and code. This is important, and we will show you how this is done. This is just a pleasant consequence of unifying the data storage, extensibility, and I can go on and on. I'm just skipping through modularity and API standardization. If you have a unified system, you can build anything on top in a single way. And of course, it can facilitate even user creativity, because the user will focus on building algorithms rather than once you get right, you don't need to reinvent the wheel to build a beautiful distributed classification algorithm on LiDAR. You just focus on the distributed algorithm and not all the peculiarities of the data systems underneath. This adds future-proofness to the system, because there's an advance in computer hardware. We're not going to rebuild the whole thing. We will just update parts of the system to accommodate the new hardware, or to accommodate new algorithms, or to accommodate any kind of technological advancement. And most importantly, there's going to be no more noise. Once we standardize everything, the scientists are going to have a single way of managing the data, and multiple ways to use this managed data. So what is the secret sauce for TileDB? You all know by now the dense arrays. I mean, you have used HDF5, you may be using SAR, file formats like COGS, effectively implement a matrix of RGB colors, right? Or something like that, something along those lines. What we're saying is that we can build an efficient system, a generic system. We don't need to invent a new format every single time that we have a different data type. As long as we can model it as a dense array, we can capture it for sure. But the secret sauce here in TileDB is that we support sparse arrays natively as well in a single system. So dense arrays for images, video, time series of images, weather, and so on and so forth, but also sparse arrays for example, LiDAR or tables or something similar. Okay, and you can imagine we took this to the extreme. We have heterogeneous dimensions. One can be string, one can be float, another can be integer in the same array. You can have cell multiplicities. For LiDAR, for example, this is important. For tables, you don't have cell multiplicities in a dense array. And arbitrary metadata. And please believe me when I tell you that once you implement a powerful storage engine and a powerful format that works very well on the cloud around this data structure, you can capture everything. And by everything, I mean, before I tell you the applications, you can have a flex to get data the data eventually stored address medium. Checking my connection, Amy. Do you still hear me? Can you guys hear me?
Yeah, it was cutting out for a second, but maybe repeat what you just said.
Go cut off a little bit.
It might be necessary for you to turn up your video, Stavros, just for the benefit of projecting.
That's what I would suggest also.
Sounds very good. Okay, so once again, the important idea here, guys, is that once you implement this, effectively you have a means to lay out very flexibly any kind of data from any application and any dimensionality on one-dimensional disk. That's what it is. And then arrays allow you to chunk the data so that you can compress, encrypt, and so on and so forth, very, very flexibly in more than one ways, depending on whether it is dense or sparse or how many dimensions you have, and so on and so forth. And then, of course, arrays provide rapid slicing, right? They provide rapid slicing from the 1D space, preserving the multidimensional locality. That's where the whole game is played, right? So the end result is that you have a single storage abstraction that everybody understands. It's very mathematical, it's very intuitive. And then you can build APIs and access control and versioning and everything else on top of this. That's the main idea. So what can we model as array? And everything that I show you here, we do have a use case for. Tables, it could be vectors, or it could be multidimensional sparse points. I can elaborate on a separate presentation. LiDAR, 3-dimensional sparse. SAR could be 2-dimensional for one image, or 3-dimensional if you have time series. Then a lot of genomic stuff that we're doing in biomedical imaging, time series of any kind, weather, again, 2-dimensional if you have NetCDF data, or 3-dimensional if you have time series of NetCDF data, graphs, video, key values, even flat files. And for flat files, I will explain soon why this is important. So this is a truly universal format, and we can efficiently store data from any application. So how did we build this? And this is where Seth and Norman are going to explain more about, and they're going to show you this in practice. So you have any backend at the very bottom, you have any API, any language, any integration, any custom application domain software at the top. That is your favorite tool and your favorite way of accessing the data. At the very bottom, we built an open source storage engine and the format, and I'm going to explain the characteristics in a bit. And then on top, we built the database features. This is the scalability, access control, Jupyter notebooks, sharing. Again, I'm going to explain in more detail soon. And we took integrations to the extreme. We are employing zero copy methods to integrate your favorite tools with our data management platform. So TileDB embedded can be found here on GitHub at the top left, at the bottom left, I'm sorry. Here are some high-level features I'm going to go through very, very quickly. TileDB is extremely performant. It's built in C++. It's fully multi-threaded. It's columnar, so that compression is more effective. We have multiple compressors. We have R trees for sparse arrays. We have rapid updates and versioning. Everything is immutable because of the cloud object stores, log-free. We have a parallel reader-writer model and time traveling. So these are very powerful features. We integrate with pretty much everything. We have 7 APIs as of today and growing, and a lot of integrations with PDAL, GDAL, and others. And of course, it is optimized for the cloud. There is an upcoming webinar on TileDB embedded where we will explain the format and why it is optimized for the cloud very soon. And that's going to be an actual deep dive. Unfortunately, every component of TileDB merits a separate deep dive workshop, which we're doing. And TileDB Cloud is the platform. This is what is going to be demoed today. In addition to the management aspects, access control, security, and all of that, it implements serverless task graphs, and Seth and Norman today are going to show you them, to show you this capability. So I'm going to skip it quickly. And again, high-level features can work anywhere on the cloud or on your premises. It is of course cloud optimized, but it can work in your data center if you have one. We do not depend on a cloud vendor's capabilities. We build our own from scratch. It is completely serverless. You can see that we can launch Jupyter notebooks, even visualization dashboards. I'm going to leave this to Seth. It is geo-aware. This is extremely important, guys, because when we talk about global scale, we mean it. So if your data is, I don't know, in Singapore, and somebody spins up some compute in a serverless manner, we send the compute to the region in Singapore next to the data. And we do all of that automatically. It required a lot of engineering on our end in order to pull this off, and we did. It is secure. We have all the attestations going on. And this is one of the most important points that I would like to make. Everything in TileDB Cloud is an array. Of course, all the types of data, as I mentioned, but even Jupyter notebooks. We store a notebook as a one-dimensional dense array, which is versioned. So you can share it and you can time travel on those Jupyter notebooks. And of course, you can make them discoverable. The same goes with arbitrary user-defined functions and task graphs. Everything is serialized in our format, it's versioned, and then you can share or monetize that on the platform. And then machine learning, dashboards, pretty much everything. So everything is shareable, everything is logged, and everything is monetizable. Okay, so this is a very, very quick overview of the capabilities and the vision. I would like to stop sharing so that I can first answer some questions. I see Sudhir has some questions, and then I can leave it to Seth.
Hey, hi, Stavros. Very exciting. Actually, I haven't looked at this one before, but I think it seems like, great solution working for especially like the challenge that we have with the formats that we deal with. So a couple of questions like, that you have. So the solution that you have, this one is this basically like, for example, when you're working with the LiDAR data, the data set, the data volume is so high, right? So like you said, that we do not need to copy the data set. So for example, if the data set sitting in the S3, how quick those data sets can be accessed first, right? And are those solutions that you have TileDB that is sit on the on a place which is like a cloud agnostic, right? That you can move across the cloud, and what are the like cost models and something like that if someone wants to give it a try.
This is a great question, both great questions. So regarding LiDAR slicing, Norman is going to show you, it is rapid. Once you store the data in the three-dimensional sparse format of TileDB, you need to forget about files, about metadata files, where is this area. Everything is a global array with global positioning, right? If you have multiple projections, we have groups of arrays, so don't worry about multiple projections. Let's focus on one for now. But imagine a massive data set, terabytes of data. If you slice any area, the cost is dominated by the result size, not by the data set size. Because of the R trees that we have superb indexing, and the slicing is just rapid. We have parallel I/O for everything we do on S3. So everything is rapid, and Norman is going to show you something on the spot today. Regarding cost models, it depends, but we charge only in a pay-as-you-go manner, which is the fairest thing for all the users. And also, this is important that I wanted to mention this, especially when you share data, you don't want to build infrastructure that services 1 million people and pay for these 1 million people. I see organizations doing it, and it's a mistake. What we do is that we're saying, listen, guys, if you share data, put it in the TileDB format, put it in your buckets, then give governance access to TileDB, and then crowdsource the cost. So if 1 million people are accessing the data, then 1 million people will pay for accessing the data, not the owner of the data. That's what we're doing. We're just a mediator. We're managing the compute on the clusters. It's very cheap because you slice for 5 seconds, you pay like a fraction of a cent, which is true. And Norman can show this to you today. So it is cloud agnostic. It depends on the compute that we get from all the providers, but we use a lot of spot, so we can drop the price. And then if you use it yourself, again, you can use spot instances, and this drops the cost drastically. We can show you, if you have a particular workload you would like us to run, we're very happy to run it, like, I don't know, a classification example or something else which is computationally intensive, and we can give you some estimations about the costs.
All right. Well, one quick question more to add on to that. So, like, in the TileDB, when we have the data multi data formats that we have, when it comes to tile, do we need a conversion that goes to the pushing to the TileDB, or how does that work?
Once again, Norman, please note this when you show it.
I'll hold on to that one. Sure.
The quick answer is
Stavros, we lost you, Stavros. Maybe we can go on to Seth, and I know, Rob, you also have a question. Maybe we should go on to Seth and Norman and finish questions at the end, if that's okay.
Yeah, and Sudhir, yeah, I saw that you lost me, guys. Norman will show you how slicing is done. It's very intuitive. You will see it in action.
Cool, thank you, and I'll follow up. Thanks.
Okay. Did we want to proceed with the demo, or Rob, did you want to ask your question first?
You can proceed with the demo if you want. That's fine. I'll lower my hand.
Okay, I'll be quick. I only need a few minutes here to show a high level, and then Norman's going to take it over with some real world examples, and then we'll try to save at least 15 minutes for questions at the end here. So I'm sharing my screen right now, and what you're seeing is TileDB Cloud, what Stavros has just talked about. A couple things I want to point out before I get too much into the demo is I'm showing you the hosted version we have of TileDB Cloud today everyone on the call can sign up for this. We give some free credits when you do sign in. And you can walk through the examples that I'm going to walk over today, or Norman's going to walk through today. Everything we're showing more or less is on the public domain. So you guys can follow along with that. It's also, this TileDB Cloud is also available for on-prem edition. The exact same thing you're going to see here today could also be used on-prem behind your own firewall and your own cluster. Also, I'm walking through the website, obviously, today, but everything is available via programmatic APIs, whether that's data slicing, whether that's the catalog information in the searching, whether that's your user profile. We provide full APIs, a REST API for everything TileDB Cloud, and then the different open source clients and the different programming languages as Stavros highlighted and discussed. So everything I'm walking through today can also be accessed programmatically. When you first pull up TileDB Cloud, we bring you to the Explore page. And this is where you can view all of the public data sets, notebooks, user-defined functions, machine learning models, and really any public asset that is in the system today. So this is a place where you can come collaborate with anyone at large on the internet to find data sets and or notebooks that might be of interest to you. So for instance, under arrays, we have a couple different data sets available right here on the front page. We have a LiDAR data set from the state of New Jersey here in the United States, which I'll actually walk through in just a second. We also have the New York City taxi data set. This is the time series data about taxi trips in New York, kind of a famous one that a lot of people like to use for time series. We've got some genomics data sets, a quick start. We have some LiDAR, we have some SAR data from Capella in the system. So we have a wide variety of data sets already in the system, public, that you can poke and explore today, dense and sparse, of all different sizes, from a few kilobytes on the experimental side, all the way up to gigabytes, and even a few that are in the terabytes range that are publicly available in the system today. So you guys can come and take a look at everything. In addition to the public arrays, we also have TileDB Cloud notebooks. And as Stavros mentioned, we have notebooks stored here in TileDB Cloud actually as TileDB arrays. So these are Jupyter notebooks, which we wrote a content plugin for, to allow storing the Jupyter notebook as a TileDB array, so you can hear all the functionality that comes with TileDB Cloud. We'll look at one of those in just a few moments also. We also have user-defined functions. These are arbitrary Python or R functions that you can store in the system, again, as a TileDB array. Everything here is a TileDB array, probably a common thing you'll see. And you inherit all the same functionality, versioning, access control for this, and allowing you to programmatically call these functions through our serverless APIs. We'll explain a little bit more, and I'm going to walk through a demo of that in a little bit. And lastly, I want to highlight also, we have a new feature we've just launched around machine learning models. So we have integrations with scikit-learn, PyTorch, TensorFlow, and a few others that allow you to actually store the machine learning model as a TileDB array. And once again, inheriting all the functionality around versioning, access control, and whatnot. We'll take a look at one of those also if time permits. To get started with, though, I'm going to pull up the New Jersey LiDAR data set just to walk through some of the features that we have here. So the first thing you'll see when we actually view the array itself is we provide a lot of high-level overview of the data of the array that's here, often things that you store alongside the data. For instance, a nice description about, like, what is this array? What does it represent? This is full markdown, so you could have images, tables, whatnot, much like a GitHub README. We also provide a variety of high-level information. You can put different hashtags to categorize the data. This is a point cloud data set, the type of the array, the size, and the permissions. So again, in TileDB Cloud, we have full level of permissions and different levels, reading, writing, whatnot. In this case, I'm the admin of this array, so I can see a few extra information. We provide you with the URI to access the array. And then also, because I'm the admin, we can actually show you where the data is stored itself. So in this case, I can see that it's stored in an S3, a particular S3 bucket right here. And it's important to point out that TileDB Cloud does not host your data. The data will always be in your own S3 bucket. So you have full control and full ownership of that data. TileDB Cloud just facilitates access to the data. So you give us permission for the governance, and then we provide all of the access control functionality through TileDB Cloud. But we're not hosting the data itself. This could be, your own S3 bucket stored in the system today. So we also provide the array schema, so you can quickly take a look at what the schema is, the filters, the dimensions, whatnot, also available programmatically. And TileDB arrays have array metadata that you can store with them. This is arbitrary key value metadata that you can associate with the array. We render it right here in the UI. This could be strings, integers, time, date times, any type of value could be here. So you can have an arbitrary amount of key value data to put with the array. Also available programmatically and baked into most of our integrations, including like GDAL and PDAL. The next thing that I want to highlight just real quick too, as Stavros kind of mentioned, is we do have monetization built into the platform. So we allow you to add pricing to your arrays or your notebooks and user-defined functions or machine learning models. So we have it baked through the entire system. So this allows you to monetize your data set. So you can add a premium to charge the users for accessing the array that you have in the system, or again, even the code that you have in the system. Happy to schedule follow-ups to do deep dives around the marketplace if that is of interest to folks on the call. We also have the full audit activity and audit trails in the system. So you can easily see who accesses the array or also the notebooks and functions, when they accessed it, what ranges or what cells of the array they accessed. All of the information is available in the system. Here we have a nice high-level summary saying, when they accessed it, what did they do, and a link to the task. The task provides the specific details, like I mentioned, including programming languages, and if it was a SQL query, potentially even like the SQL function that was run, or the Python or R function that was there. Norman will take a look at one of those in just a little bit. In addition to the activity, we also have these sharing permissions, and this is where the collaboration really comes into play. So we make it very, very, very easy for you to collaborate with other users or coworkers on a particular data set or the notebooks and functions and machine learning models. So to share your array, you simply click the share button. I could type Stavros here. I select Stavros. I can give him the permissions I want: read, write, read and write permissions. And if I click share, he would then instantly get access to the data. And how this works is we're not messing with S3 bucket policies. You as the user don't have to manage S3 bucket policies. You as the user aren't managing IAM roles. Instead, inside TileDB Cloud, we manage all the access control policies through the service. And when a request comes in, we check and validate that access and then facilitate the underlying access to the storage. TileDB Cloud is the only thing that will ever access the underlying storage. We never give direct S3 access to the end user, so it's a very secure system that we have here. And it makes it super simple. You can share it with another user, with another organization, with just a click of a button. Again, you don't have to manage the underlying bucket policies or details there. We also make it very easy to make your data set private and or public. Right from the settings page, we have a setting where you can toggle the behavior. So you can share it with individuals, or if you have an example data set, you can also make it public and share it with the internet at large. For the sake of time, the last thing that I want to show real quick, just because it did come up, is the notebooks. The user-defined functions and machine learning models work very similar to the notebooks, but since there was a lot of talk around the collaboration with the code and notebooks, we do have them fully baked into the system here. Again, having all the similarities around TileDB arrays, description, hashtags, you can put licensing, and you can share it and you can view the activity just like a TileDB array and just like what I showed you. But you can also view a rendering of the notebook itself. So we have a static rendering available in the system. So if you want to share it with someone, they can come in, they can view the notebook, they can even see output from the notebook directly without running the code. If they like it, or if they want to make tweaks, you can simply click the launch button and go directly into a live Jupyter Lab environment to then run the actual code and go through. Norman will run through some live demos of using these notebooks for that purpose. Norman, if you'd like to take it away.
Thank you, Seth. Thank you, everyone. It's good to be here. I'm just going to share my screen in a second. I'm not going to share a video because I think the connection's a little bit unstable. So you should be able to see a notebook environment now. And I'm going to cover a wide range of use cases in about 5 minutes. So we're going to show you some LiDAR. We're going to show you how to ingest that LiDAR data set. And then we're not just sparse arrays, we also do dense arrays. So I'm going to show you an example of hyperspectral and also with SAR. And then we're going to do a mapping of AIS data with SAR data, and then show you how you can do dark shift detection. We're going to be using a variety of data here. Some of the data is from the work we've been doing with Capella Space and also with ESIP. So Seth touched on the fact that we had a LiDAR array, and he went over the example schema. You can see here that we have X, Y, and Z, and then we have an arbitrary number of attributes. So we're a multi-dimensional database, and we allow you to compress each one of those attributes separately. So you can use bzip, C standard, whatever you want there to go and optimize for read or write. The syntax for doing a quick read is here for a data frame. We're slicing a region from a LiDAR dataset directly. You can either read this locally or you can read it directly from cloud storage. Here you can see the data frame. And then we plot that data directly in our notebook, either in a 2D matplotlib function or as a Babylon.js, so a 3D interactive viewer directly here within the notebook. You can also run SQL, serverless SQL on this LiDAR dataset, as Seth mentioned. So here you can see the syntax here for doing serverless SQL. And you can see here we got a count. In terms of doing queries directly in the cloud, this is how you define a user-defined function. It's just a Python function in this case. And if you want to do a slice, well, we're slicing here on just on X because we know this data set in this case is just a street. And we're going to ask for all the Y and all the Z, and that will give us building number 3. You can see the schema again. This schema is auto-populated by using our PDAL integration. And we retrieved 100,000 points directly from the cloud storage in just under 4 seconds. We then plot that data, put it into a data frame so we can do statistical analysis and remove any outliers. And then we also run DS1 again in 3D. So in terms of doing ingest, one of the common things you want to do with ingestion is ingest multiple files at once. So TileDB allows you to append in parallel. And you can see here that we have 150 gigabytes of LAS files. It's going to create a 55 gigabyte TileDB array, and we're going to ingest this in parallel. So 20 files directly from S3 into a TileDB array. And we did that in about 2 minutes. So you times that by it normally take you an hour and a half or so to go and do this serially. So now we're going to look at a hyperspectral use case. So you can see here we have an array that's already registered. It's from the Neon group. We print the schema, its bands, and its Y and X. You can order these any way you want. For hyperspectral, it's useful to be able to index on bands first. You can see in this case it is hyperspectral. It has 426 bands. We're going to extract the visible RGB in this example. And then for SAR, we have a whole collection of SAR data, and we're going to slice an area of interest in AOI. We're going to register it and stack them, and then we're going to do visible change detection. So here you can see container ships moving around the port of Rotterdam. And then finally, for dark ship detection, we have AIS data here. This is from the month of August in 2019. And we can see the schema. We can see how it looks in a data frame. We're going to register this over a quick map so we can make sure that data lines up correctly. And then we're going to line this up with a SAR scene. So you can see here. So the benefit of SAR is that SAR sees through clouds. So if you have the AIS data and you have the SAR data, you can register them together and you're guaranteed to see the ships. If you couple this with the nighttime lights data set, then you're going to be able to identify any ships that aren't broadcasting when they should be broadcasting. So this leaves us about 10 minutes for questions. Amy, I'll hand back to you.
Cool, thanks so much. That's really cool stuff to see. I love seeing those visualizations. So let's see, I'm going to just repeat some of the questions that were pasted in the chat. I think Seth and Stavros, you already answered a number of the questions that were in the chat, so thanks for that. So one of the questions that wasn't answered yet was, how does TileDB work with near real-time data such as features?
I'll take that one if Stavros isn't going to take it. So with TileDB, we definitely support near real-time data, and I think it just kind of depends on what your data format is based off how we would handle that. But what source the incoming data is. But in near real time, it's very easy to write to TileDB. Every write is an immutable write. So unlike certain other file formats, when you're updating an array or appending to an array on a cloud object store, there's no problem with incremental writes to the array. Now, we do have processes for what we call consolidating the array. if you're writing a small amount of data over time, you can consolidate that to produce larger, what we call fragments. So you can group the data and potentially consolidate some of that, or purge out old data from the system, all available through there. So having near real-time data is not a problem at all in the system. And usually, however you're trying to do it, again, you can write individual records, although we strongly recommend batching records for performance reasons. But all of our different systems support appending to an existing array and or inserting or updating the values depending on, again, the schema and the format.
Yeah, I
Okay,
just had. Sorry, go ahead.
No, that was my question actually. So, if we have the feature classes, so with millions polylines that we have in the data, in say if we also store in NetCDF, how it's going to behave, because those polyline also has the connectivity attached to it, and how does it? I'm just trying to understand how it works in the back end.
So we have examples of doing this, not with polylines, mainly with points. So both LiDAR and sonar, and we allow you to write at a particular timestamp, and you can just go and sync that data from your local storage to the cloud storage, and then have it available in the notebook. I'm actually going to be presenting on that at phosphorouge next month, but we can have a deeper dive on that as well on this call.
Oh, thanks, Norm.
Norman, what's the name of your phosphorouge talk?
I think deeper dive with sonar, I think. And then Julia from our team is presenting on NetCDF with TileDB.
Oh, okay, cool.
We also have a workshop. So we have a 4-hour workshop at phosphorouge too.
Oh, okay, great. And I think that touches on one of my questions, which was basically for these archival formats. It sounds like there's some sort of toolbox for indexing them into TileDB. Does it require sort of duplicating, not, I don't want to say duplicating, but does it require creating a new storage for that data, or are you just creating metadata on top of the archival, like NetCDF formats?
No, we do require that the data is translated to the TileDB format. You only have to do it once. People are finding it very easy to do, particularly using a task graph. It's very quick, and then you get all the benefits of TileDB afterwards.
Rob, do you want to ask your question?
Sure. Yeah, that kind of just tacks onto what you were asking, Amy. Really, I was curious about the size that indexing adds to the cost of storage. So if you have, based on whether you have a small archive you have in the database, or you have a very large archive, is there any kind of guidance or message you have regarding the indexing size that's present?
Yeah, this is a good question. Here's how it works. When you store data into a sparse array in TileDB, not a dense array. For dense array, the indexing is kind of implicit. You don't need an index structure, because we know that every tile is fully populated, and because we know the tile extents of that tile, then we can infer pretty much every cell slab that falls into your query. We don't need to store extra information. And HDF5 and ZAR do something similar. But for sparse arrays, because you don't know where the non-empty cells are, we use an R tree. And here's how it works. When you store data in TileDB, you provide the data in a batch. For example, you populate, I don't know, memory buffers of size, let's say a couple of gigabytes. And you just give those to TileDB, and TileDB is going to sort the data based on whatever order you have specified in the schema. One order, for example, is Hilbert. So TileDB is going to sort the data, and then it's going to create an R tree in a bulk loaded fashion. So it's going to take the sorted data, it's going to chunk the data based on your tile capacity. This is a schema parameter. Usually we suggest that it's going to that it should be between 10K and 1 million. So 10,000 to 1 million non-empty cells in a data tile. And then we just scan those cells per tile in parallel, and we're creating bounding boxes, one bounding box per tile. And then hierarchically, we store bounding boxes we group bounding boxes together to create other bounding boxes, and this comprises the R3. The computational timing for doing this is negligible because it's the time is dominated either by the I/O or the compression time. So just creating bounding boxes on the coordinates is rapid. And then in terms of size, it's also negligible based on the factor that you choose for your tile capacity. So if it is 10,000, you're reducing the index size by a factor of 10,000. If it's 1,000,000, you're reducing the index by a factor of 1,000,000. Does that make sense?
Yes, I get the sense it's kind of a boxes within boxes, sort of fractal type of indexing.
Correct. Very, very lightweight, but it has proven extremely efficient, especially if the underlying order is effective. So for LiDAR, for example, Hilbert works. For, I don't know, for genomics, it doesn't, because for genomics, you want to slice giving more preference, for example, to a position versus a sample, like, you know, one dimension over the other. Hilbert doesn't prefer one dimension over the other. That it's trying to give equal preference to all dimensions. But in other scenario, you don't want this. You really want the data sorted on one dimension better than another.
So, Stavros, one quick question. I think that's maybe I may need to find a follow-up with you. But like, you know, if we have a large set of data sets sitting on the S3, I think that then if, you know, we want to have it go through the TileDB, you know, how much space are we talking about? Like, do we need to stand another, you know, do we need to be paying for other larger space because it needs to get converted into TileDB? Or what is the residence time that it needs to be converted? Does it need to be converted everything at once, or it converts on the fly or on the demand, or how does it work? Sort of like just a generic basic question, I guess.
Yeah, so TileDB ingests in batches, right? It can even ingest a huge NetCDF data set box by box. One box and another box, or at one time instant, another time instant, and so on and so forth. So that's not the problem. It can be done incrementally. The question is, the point is that you need to duplicate your data set eventually. So you have one NetCDF data set. This whole thing needs to be converted to TileDB whenever you want to slice it. If you want to slice a part of it, you need to convert a part of it. But if you want to slice it in an ad hoc manner in its entirety, obviously you need to convert the whole data set. And then, of course, you can delete the NetCDF data. What I want to tell you from experience from other domains as well, like genomics. In genomics, they have massive data sets, as massive as the weather data. They do it once, they get rid of the other data, the original data. TileDB compresses better because it's sparse, because it uses different compressors per field. So it chooses the compressor wisely. And they usually see a huge reduction, like 60%, 70% on the data. So I would not worry about the storage, especially if it is one-off. I would really worry about compute in an amortized way over the course of the year.
Okay, thanks.
Awesome. Okay, well, we have time for one more question. I see Vishu, you raised your hand. Let's see if there's anybody else have a question, just so we get anybody that didn't get a chance to ask a question earlier. Okay, yeah, Vishu, why don't you ask your question?
Yeah, hi, thanks for the presentation. It was very informative. I come from a time when DB2 was doing spatial extender, trying to get all data into one single database system and all that stuff. So I'm all in for the universal, query across all databases and stuff. But I do worry about storage. I know you said don't worry about storage, but I do worry. So LAS, for example, is already compressed pretty heavily, right? So when you do an ingest into it, I have a bunch of questions. One is, what is the overhead on ETL? How long does it take? And what is the bloat size? And when you say TileDB does a lot of compression way better than others, I know you gave the example of genomics, but what happens in the case of LAS? Is it a good enough compression? How would you compare it, say, like 10 gig LAS file when it's in TileDB? What is the size there? And are we paying for those costs? Thanks.
Yeah, and I understand the issue because especially for LAS, if we're talking about massive quantities, and I mean LAS, we actually compress better. LAS, LAZ is.
Oh, we lost you, Charles.
Sorry, yeah.
Yeah, so I can answer that question myself as well. So LAS, we compress way better, like 3 to 1. For LAZ, we don't compress as well as LAZ. It's hard to compete with LAZ's floating point compressor for time, GPS time in particular. So there's a bit of overhead there. But you can't slice LAS or LAZ directly from the cloud, and you can with TileDB. So it is worth that trade-off.
So sorry, a follow-up to that question. So when you're compressing that, you're obviously compressing it based on a particular use case for a particular set of queries. What if the query changes?
Hey guys, did you get any of this? My internet gets interrupted without notice, without telling me you're about to shut down.
Yeah, so we answered the question, Stavros. The follow-up question was, could we change the compression depending on the query?
Depending on the query, no, right? Because you store
Right.
once. Upon ingestion, yes. And actually, if we do see that this is a huge pain for the organizations trying to store LAZ files in TileDB, and they say, no, we want the same compression as this, what we need to do is that we need to implement the same sorted float compressor of LAZ. This is in the public domain, it's documented well, but we will just have to do this custom compressor. The good news is that we don't need to change anything else. And this is, this kind of proves my point about the extensibility of the universal database. You don't need to build another format, you need to build another compressor, and then you just plug it in. So if this indeed becomes a huge problem, we're up for implementing it.
And then just going back to the overhead of ingestion, I showed you an example, but very quickly, that we allow you to ingest in parallel. So if you have 20, 50, 100 LAS files, LAZ files, you can ingest those using our task graphs, and we scale to the amount of compute that you want to use.
I think Alexander had a question, if he's still here, if he wanted to ask it.
Oh, thank you. Thanks, Amy. Very quick one. I apologize, I missed that. That SQL query that someone showed in the notebook, did that comes for just with TileDB, or actually some kind of a plugin that you need to have?
I'll take that one real quick. So we have a couple different ways to run SQL queries on TileDB. In TileDB Cloud, starting with that, we have serverless SQL, meaning that you can provide the SQL query and it will run in the TileDB Cloud service, managing all of it for you without you having to spin up a SQL database or cluster or anything like that. We support ANSI SQL and parameters and everything you can imagine there. Happy to schedule more time to dive into that. The TileDB Cloud SQL is powered by our MariaDB storage engine that we have written. So we have an integration with MariaDB where we wrote a storage engine through their storage API that allows us to access TileDB arrays directly and then return the results through the MariaDB ecosystem. So MariaDB parses the SQL, gives us the tree. We take parts of the AST tree there and perform a highly efficient SQL query. We also have integrations with Spark and Spark SQL and Presto DB for distributed Presto SQL there. So what was shown in the notebook was through our MariaDB integration. MariaDB can also be run through an embedded mode. So you can run your own MariaDB server like most people are probably familiar with. We also have a build for an embedded library, so you can use it directly from Python or R, just like you do TileDB as a library, or we have our serverless SQL offering to let TileDB Cloud manage it all.
Thank you very much.
Very cool. All right, since we're over time, we should probably wrap things up. So thanks again so much to Seth, Norman, and Stavros for presenting and for everybody attending. yeah, thanks everyone for joining, and please reach out if you have any questions.
Thank you, Amy, once again. Thank you, everyone, for attending. And please reach out to us for anything, concerns, questions, insights, feature requests. We're very happy to continue the dialogue.
Cool.
All right, thanks, Stavros. I think I'll reach out.